Let's say you don't have a function and you want to find the derivative. All you have is a collection of points. How do you find the slope of the tangent line when all you have is a collection of points or a table? Well, this is climb time, and in this video, we're going to look at how to estimate the derivative when given a table or a collection of points. So you can see right here, we have a table with time and Fahrenheit. This is going to be your temperature. And this is what the graph looks like. It's kind of nice to have a visual of it so we can see what it looks like. So time is on the x-axis. So we got 0, 10, 20, 30, 40. And your temperature in Fahrenheit, 65, 95, 142, 168, 182. This would be the temperature of a potato in an oven. So while the potato's temperature is increasing, it is not increasing by as much over time because eventually the potatoes can get as hot as they can possibly get. So there is no curve here. I mean, we could connect the lines and kind of make it look a little bit like a curve, but there's no curve. How do we find a tangent line when there is no curve? And this, let's say specifically, we're trying to find the derivative at 20. So what we're looking for is f prime of 20. What is the slope of the tangent line when x equals 20? So, or t in this case, is 20. So this is going to be t, 20 right here. So this is 20. What does the slope of the tangent line look right there? Well, there's no curve. So hard to draw a tangent line when there's no curve. What we can do is we can connect these 2 points. And those 2 points could make a line, and we can find the slope of those 2 points. We could also connect the 2 points from here to here, and we can make a slope for that. And then a third option is to make a slope from here to here. So let's look at those options. So this is a slope, call this M2, and that is a rate of change. It's going to be a change in Fahrenheit with respect to time. And then this is M1. So we have an M1 and we have an M2. We can find each one of those. But the actual slope of the tangent line is not going to be the green one. It's not going to be the orange one. It's going to be somewhere in between. So what we could do is we could take the average of the green one and an average of the orange one. And that should give us hopefully something very close to the slope of the tangent line. And that would be an approximation of f prime of 20. So let's take a look at what that would look like. So if we looked at from 20 to 10, so that's the green one here, or 10 to 20. For the interval from 10 to 20, we could have the slope, we'll call this M1, and it's going to be equal to f of 20 minus f of 10 all over 20 minus 10. That's how you find the slope from here to here. And if we look for those values over here, by the way, you can plot these points on a TI-84. I have another video if you want to see how to do that. It's kind of nice sometimes to look at things visually without having to plot them by hand on graph paper, but to actually plot those points on a graphing calculator is helpful so you can see what's happening. And you can see that the difference in y values goes down over time. Even though they're always going up, the difference is going down. So if I plug that in, I'm going to get, or down plug it in, I just look at the table. F of 20 is 142. F of 10 is 95. And then divide that by 20 minus 10, which is 10. And you end up with 47 over 10, which is 4.7. So what that tells us is the slope M1 is 4.7. So it's positive, which makes sense. It's going uphill. Now, if we go to find the orange one, we would expect it to be smaller than 4.7 because we can see that it's not as steep as the green one. The orange one is less steep. So that would be from 20 to 30. And if we did that, that'd be M2. So that's going to be f of 30 minus f of 20 all over 30 minus 20. And f of 30, if we look at our table, we can see f of 30 is 168. F of 20 is 142. and that's all over 10. And the difference of those look like 26. 26 over 10 just comes out to be 2.6. So not surprisingly, the orange one is still positive. It's still going uphill. So it's still positive, but it is got a smaller magnitude than 4.7. It's less steep. The green one's steeper, the orange one's less steep. So then our actual slope of the tangent line, f prime of 20, could be approximated then as the average of those two. So let's use another color. How about blue? So we can say f prime of 20 is approximately equal to the average of m1 plus m2 divided by 2. So we average these two out, we'd expect to get the slope of the tangent line right there at that spot. So if I did that, I have 4.7 plus 2.6 and divided by 2. And let me check, make sure I get this right, 3.65. And so not surprisingly, the slope is right in between the green one and the orange one. The blue one is right in between the two. Okay, and the unit for that is, if this is Fahrenheit, so this is degrees Fahrenheit, and this is seconds, it'd be degrees Fahrenheit over seconds. So that means it's changing 3.65 degrees Fahrenheit every second. If in fact the unit here was seconds, and this was in degrees Fahrenheit. So that means every second it's going up 3.65 degrees. That seems like a pretty fast increase, but if that is in fact our units and these is in fact our data, that would be our approximation. That's why we have squiggly lines here. This would be our approximation of our derivative, or the slope of the tangent line. And the approximation is an average of the two slopes, the one in front of it and the one after it. So the one right before it, coming into that point, the one right after it, leaving that point, and the average of those two slopes would be an approximation of the slope of the tangent line. And what I like to point out is there actually is a faster way to do this. So there is another way to do this that's faster, that gives you the same result. And that would be, what if we took just the slope from here to here? So we used, maybe I can make those dots a little bit bigger here. Maybe this dot is now a little bit bigger, and this dot's a little bit bigger. What if I took just the slope from 10 to 30? What would happen then? Turns out that the slope from 10 to 30 would be exactly the same as the average of two slopes from 10 to 20, 20 to 30. And that only works though because the interval is the same. So if the interval is the same, so if you have a difference of 10 here, which we did, it's 10 to 20, and a difference of 10 here, so we have a difference of 10 and a difference of 10. So if those differences are the same, then you'll get the same result if you just find the slope from 10 to 30 as averaging 10 to 20 and 20 to 30. So let's just show that comes out to be the same thing. So f prime of 20 would be approximately equal to finding the slope from 30 to 10. I'll just put a little subscript here, 30 to 10. Would it look like this? 30 is 168. 10 is 95. And the difference between 30 and 10 is 20. Okay, so if we did that math, you get 168 minus 95, which is 68 plus 5, which is 73. And that comes out to be, once again, 3.65, the exact same answer. The unit is the same, degrees Fahrenheit per second. So two ways to do the same thing. We could either average the two slopes, the one coming into the point and the one leaving the point, or we can take the slope of the overall average, overall average slope of the 2 points on either side, like we did here. But again, this only is equal to this if the interval is the same. So if the difference here is the same as the difference there, then they'll come out the same. And it's not too hard to prove that. You can kind of see what's going on. If you average two things together, basically what you're doing is you're adding the two values together. So if you add this one to this one, they have a common denominator because their intervals are the same. And what happens is the 142s cancel out. So that's where the 168 minus 95 comes from. Because of a common denominator, then that divided by 10 would still be there. But then because we're averaging, we divide by another 2, and that's what makes it divided by 20. So you can kind of see why that works. But again, the only way that would work is if these were both 10 so that you'd have a common denominator. So your interval has to be the same to the left of the point we're interested and to the right of the point we're interested in. So if you only have a table of values and a collection of points, you can estimate the slope of the tangent line or the derivative by looking to the left and looking to the right and finding the average of the two, or picking 2 points that are equal distance away and finding the slope between those 2 points.